This next section focuses on solving polynomial functions by factoring. We were using synthetic division before, which is obviously a great method, but sometimes you just have to factor it. It's quicker. You don't have to guess and check or anything. You just go for it. So the 4 problems I'm going to do are all factoring problems, but I would like to use it as an opportunity to review more difficult factoring type problems. So the first one, we have f of x equals x cubed plus 5x squared minus 4x minus 20. And as you can see, we could use grouping here. So if you factor out an x squared, we get x plus 5. And we factor out negative 4, we get x plus 5. Again, by grouping, this must match. When you group, you should be able to pull out another GCF, and this GCF being x plus 5. If we pull out an x plus 5, we're left with x squared minus 4. X squared from this term, and minus 4 from that term. So therefore our answer is x plus 5, x plus 2, x minus 2. If we find the zeros, we get x equals 2, negative 2, and negative 5. All linear roots, all single roots. So therefore when we do our sign analysis, we should get a sign change for every single one of them. You plug in a point like 5, positive, 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 so that's positive. Plug in 0, positive, positive, so that's negative, so you can see a sign change there. When you plug in negative 3, positive, negative, negative, positive, and you can see it is going to form that sort of pattern. So the graph of this function would look like, very roughly, be a negative, then positive, then negative, then positive. The stereotypical cubic function. The next one is more interesting to me. We have 2x squared minus x squared minus 3. This here we have to treat almost like it is 2y squared minus y minus 3, where y is equal to x squared. So when we factor this, we get 2y minus 3 times y plus 1, which equals 0. So y is equal to 3 halves, or negative 1. It's important to understand that y is actually x squared. Many of you, and I know normally when I do this, I jump right to it and just say 2x squared minus 3 times x squared plus 1, and that is fine. I just wanted to kind of introduce this kind of notation, which is useful in chapter 5 when we get to there. So when we solve this, we now have x squared is equal to 3 halves, and we have x squared is equal to negative 1. This here, when we take the square root, we get plus or minus I, so we get 2 imaginary roots. So those will not show up on the graph. Over here, we get x equals plus or minus the square root of 3 over 2, which if we rationalize that, we get the square root of 6 over 2, plus or minus, which is approximately 1.22. Therefore, this has 2 roots. If we do our sign analysis, we cannot put plus or minus I on it. We have negative 1.22, and we have 1.22. And if you plug values in, you'll see the sign analysis is positive, negative, then positive, giving you a graph. Again, I'm very roughly sketching these. Positive, it's negative. It does a little thing like this down here. How would you know that? I just know from looking at the graph and from experience that's what's going to happen. Obviously, given the sign analysis, you would not be able to tell that, but in calculus, when you further analyze these graphs, you'd be able to pick up on this behavior in between. Since it's quartic, it makes sense because it makes a W shape. So the final 2 problems, first one is similar to the last one. If we factor this again, now I'm going to jump right into it. You get 2x squared minus 5 times x squared plus 4 equals 0. Again, we get x equals plus or minus 2y on this one. On this side, we get x squared is equal to 5 halves. So x equals the square root of 5 over 2, or the square root of 10 over 2, plus or minus, of course. Due to the fact that it's pretty much very similar to the last one, I'm not going to graph that one. It's basically identical, except the x value obviously is slightly different. On the last one, I have an x to the 6. Again, you could treat y is equal to x cubed in order to get a quadratic nature. If you do that, you have y squared minus 7y minus 8 equals 0. So when you factor that, you have y minus 8 times y plus 1. So when does x cubed equal 8? And when does x cubed equal negative 1? It's x equals 2 and x equals negative 1. So if we sketch a sign analysis, you can punch numbers in. Punch numbers like 5 in there. You can see that this is, if I rewrite this, it will be easier to tell. If you plug in 5, that's going to be positive, that's going to be positive, so that's positive. If you plug in 0, you're going to get negative. And if you plug in negative 2, negative and negative. So the graph should look like that. Something does seem off. Just trying to double check my work there. If I punch in negative 2, this one's definitely negative. Punch in negative 2, that one's negative. If you punch in 0, it's negative. That looks fine. Okay. Therefore, this graph would have to have a double root at negative 1 and a single root at 2. So be negative, bounce back down, and then who knows what it's doing in here. It could be doing a multitude of things. It could be doing like that. It could be, I don't know unless I look at the graph, but it could be doing a lot of different things unless I perform calculus here. I don't really care. I care about what's going on here and here for now. So I can see that it is negative, negative, and then positive after. And that's all that really matters to me at this point. And that wraps things up for this mini lesson on solving polynomials by factoring. I'll see you tomorrow.